In this video, we'll cover the lifetimes of excited states and selection rules and end up with Fermi's golden rule. We'll start by discussing the lifetime of an excited state. Then we'll look at the allowed transitions, Fermi's golden rule, and finally, forbidden transitions. So suppose that you make it possible to pump a large number of atoms into the excited state psi b. Again, it's a two-level system, as before. Because of spontaneous emission, the rate that we calculated in the previous video, this number will decrease in time, and it's linear with time. And so d sub nb by dt is equal to minus a times n sub b, where a is the Einstein A coefficient. Well, this differential equation can be solved by direct integration. You divide by n sub b, and you have dnb over nb equals minus a dt, and you integrate that out. This is the equation that you end up with. You can integrate this. This is an exact derivative of log of n sub b, natural log of L sub b, and this just gives you minus a times t. So you have natural log of n sub b is equal to minus a times t plus an integration constant. When you take the antilog, you get that n sub b is equal to e to the minus at plus my integration constant. And if I separate these two, I have this is equal to e to the c power times e to the minus at, and this is just a constant because e to a constant is a constant. We'll call that constant n sub b at time equals 0. So n sub b is equal to n sub b at time equals 0 times e to the minus at. So it's an exponential decay due to a linear decrease, which is due to a constant rate. We can rewrite this in a way that's a little bit more descriptive. N sub b of 0 times e to the minus t over tau, where this is the lifetime. So tau is equal to 1 over the A coefficient, and it's called the lifetime of state psi b. Now, if the atom has a lot of decay modes, not just the one to state A, but there's other ways that you go from state B down to state 1, 2, 3, or whatever, then the total lifetime is a composite quantity. Tau total is equal to 1 over a sub 1 plus a sub 2 plus a sub ... all the way to a sub n. That means that these lifetimes add in a very specific way. 1 over the lifetimes adds up as sums. Now, that's all well and good, but which transitions are allowed? Well, we covered this previously when we talked about symmetry, but we'll go over it again very quickly. So determining these allowed transition means you have to compute matrix elements. And the matrix elements you want to compute are those of the polarization for electromagnetic radiation. So you have psi b, inner product of psi b, r vector psi a. And most often these are just 0. There's only a few usually that give you non-zero values. For the hydrogen atom, the matrix elements can be expressed in terms of the good quantum numbers of the system before you do spin orbit coupling, and that is n prime, l prime, m prime, and nlm. So this is the nlm basis set. And this inner product then is you have the 3 primed quantum numbers over here and the unprimed quantum numbers, and you have r vector in the middle. Well, we calculate these using symmetry considerations, and we know that this leads to selection rules. And the selection rules are that delta L is equal to plus or minus 1. Delta M is 0 or plus or minus 1. And so we can draw a diagram here which shows what transitions are available. So for example, at n equals 4, when you have L equals 0, you can go up by 1 in L. So you can go to L equals 1 from n equals 3, always dropping down at least one value of n, or to n equals 2 and L equals 0. And so on. You see all these different transitions, and we covered those previously when we were looking at symmetry. Now, if you want to note something, is that this level here, the n equals 2, L equals 0, m equals 0 level is stuck. It cannot decay anywhere. Every other level can decay down, but this one cannot decay directly. But it will decay eventually through other channels like thermal de-excitation or something like that. So the spin of the affected electron when you have a transition doesn't change. So the transitions to partially filled levels can be inhibited, right? Because the selection rules don't say anything about S or M sub S. They only say about delta M sub L and delta L. So what happens is that if you have some levels that are possible to decay to, but they're filled, that will inhibit the decay. Now, let's suppose that you have a transition of an electron from a discrete state to a continuum of states. And all these states satisfy the selection rules. So you have your initial state energy down here, your final state energy is up here, and there's a whole bunch of states in here, all these green states, that satisfy this, the selection criteria, the selection rules. What you want to do then is to calculate the transition probability of an initial state of energy E sub I, making a transition to a state within a finite energy range, delta E, around E sub F. Because of uncertainties in the energy, you can have a band over which this transition can take place. And you can do that by doing an integral over the density of possible final states. So, this transition probability P is an integral from EF minus delta E over 2 to EF plus delta E over 2 of the potential for the matrix element that goes from state I to the final state n, modulus squared, over h bar squared, and then sine squared of omega sub 0 minus omega t over 2, divided by omega sub 0 minus omega squared, times the density of states. This is the number of states with energy E sub n, and then you integrate over E sub n. So omega sub 0, of course, is E sub n minus E sub I over h bar. That's the angular frequency of the transition energy. Rho of En, dE E sub n, is the number of states between E and E plus delta E. And rho of E sub n is just the density of states. So in this case, it's more than a simple two-level model. There's a bunch of states that you can transition to because they all satisfy the selection criteria. But similarly to the simple two-level model, at long times t, the integrand has to be sharply peaked around the energy difference such that EF minus EI is equal to the energy of the photon. So the energy of the photon sort of sets what the final energy is if you know the initial energy. You can then take this integral and simplify it. Well, clearly this matrix element is already just a scalar, so you can pull it out. So it's V from the initial state to the final state, and because it's this, the energy density is peaked very heavily around the final state energy, you can replace V sub In with V sub If. And you can replace rho of E sub n with rho of E sub f, simplifying the integral. You can then assume that because that distribution is very narrow, the limits of integration can go from minus infinity to infinity instead of a finite distance away from the final energy. And now you just have to integrate this same quantity which we've integrated before, which is sine squared of omega sub 0 minus omega t over 2 divided by omega sub 0 minus omega quantity squared integrated over dE sub n. When you do that integral, you get 2 pi over h bar, the matrix element VIF from the initial to the final state over 2 modulus squared times the density of states at the final energy times t. So the probability increases linearly with time. The transition rate, which is the derivative of this, is constant. It's just 2 pi over h bar, VIF over 2 modulus squared, rho of E sub f. Now, Fermi's golden rule states that the transition rate is proportional to the matrix element squared times the density of states, right? And that's exactly what we figured out. This is the matrix element squared, and this is the density of states. So we can see how that works by looking at X-ray absorption. We're specifically interested in the L3 edge. Now the L3 edge means that you take a state from the, an electron from the 2p state up to a d state. Because delta L has to change by 1, you go from 2p to 5d. And there's a transition there where there's a white line peak just at the edge, which is due to the fact that you might have, or if you have some empty d states. Because if you have empty d states, these are very narrow, and they'll give you a nice sharp density of states at the absorption edge. You can see how this looks with 3 specific elements in the periodic table. Tungsten, W, is way over on the left side where you have lots of empty d states. And you can see this white line that happens at the edge jump, right at the edge of the absorption, is huge because there's a lot of states in here that this electron from the 2p level can go into. And so therefore you're proportional, because you're proportional to the density of states at that energy, you get this huge absorption. If you move to the right in the periodic table, you start filling in the d states. Well, platinum has maybe 1 or 2 empty d states. And you can see that the absorption white line is much reduced compared to that of tungsten, just because you have fewer d states. Finally, you move one more over to gold, where all the d states are full, and you have virtually no bump at the white line position, because there are no states in which that 2p electron can go into that are localized in the 5d level. Instead, it goes into the continuum, so you have a nice smooth jump, and then constant value. Now, the transition rules that we discussed now, the delta L is plus or minus 1, and delta M is 0 or plus or minus 1, are dipole transition rules, electric dipole transition rules. And we obtained them by making the approximation that the electromagnetic radiation has a wavelength that's much longer than the size of the atom. Now, in fact, that's not a necessarily good approximation. So, in fact, we'll see that you have additional terms that we have to take into account. What this approximation does is it takes the expression for a traveling electromagnetic plane wave, which is e to the I, well, e sub 0 times polarization vector z hat, e to the I k dot r minus omega t, that's a traveling wave. And we approximate it with the first term in its expansion. Right? The expansion for the exponential in k dot r, you can pull out the e to the I omega t, minus I omega t, is 1 plus I k dot r, and then the second term is this term squared, and the third term is cubed, and so on. But if we take the first term, that's the perturbation that we calculate all our matrix elements on. that is K dot R. All the terms that are represented by the dot, dot, dot here are so-called forbidden transitions. Not because they're truly forbidden, but because they're not in the dipole approximation. The first term of which is the quadrupole transition. So the selection rule for the quadrupole transition are a little bit different. You have delta L equals 0 or plus or minus 2. Delta M is 0, plus or minus 1, or plus or minus 2. And delta M sub S, of course, does not change. The spin doesn't change. So delta M sub S is equal to 0. Now the transition probability is order of the fine structure squared smaller than the dipole transition probability. So it's really quite a bit smaller because the alpha is 1 over 137, so alpha squared is 4 orders of magnitude smaller than the dipole transition probability. Nevertheless, it exists. So if we look at more absorption edges in vanadium compounds, we can see evidence of this. You have the main rise, which is due to the dipole transition from the 1s core state to a p-like state. So this is vanadium metal. As you increase the oxidation state of the metal, the nuclear screening decreases and the ionization energy increases. And at some point, when you get to, say, V2O5, you see this very sharp transition here. But even before then, you have transitions here, these two little bumps, at V2O3. And these transitions are quadrupole transitions. They come before the main edge jump, and they are the forbidden transitions where you're going from the 1s core electron to localized empty 3D states. And this is particularly visible in the V2O5 and this lithium vanadiphosphate, where you really see those d electrons, and there is more empty d electrons in the V2O5 than in the V plus 4 state. And that's why this line is much higher. So the size of these pre-edge peaks, in fact, correlates with the number of empty d states, and as well as the local geometry because of crystal electric fields.